Hello, Mr. Butts here. I want to take a look at a couple examples where we're finding volumes of solids of revolution using the disk method. So the idea here is we're taking a function and we're going to revolve it around an axis, and that's going to give us some solid, and we want to find the volume of that solid. So first thing I'm going to do on a problem like this is I'm going to make sure I know what my axis of revolution is. So that's going to be the x-axis in this example. So I'll usually draw like a little arrow circling the x-axis. And I like to include a Riemann sum rectangle and think about what's going to happen as that rectangle revolves around the x-axis. So that rectangle, as it revolves around the x-axis, because one end of the rectangle is touching the x-axis, is going to create a circle. So what we want to do to find the volume is find the area of that circle. Well, that's going to be the radius, and with the x-axis being our axis of revolution, the radius is just going to equal the function, which is the square root of x. So to find the volume, we're going to use that formula, pi times the integral from lower limit to upper limit of the radius of x squared dx. So remember the parts of this formula, where they come from. So the pi r squared, that's the area of one slice, one cross section. And then the dx, that's the thickness of a cross section. So that gives us the volume of one cross section, and then the integral sums up those volumes to get the volume of the entire solid. So in this particular example then, we're going to have pi times the integral. Now we're going from x equals 0 to x equals 4. Okay, so along the x-axis, which we need x values here, so we're going 0 to 4. And then the radius is just the square root of x. So we have the square root of x squared, because we're taking the radius squared, dx. So simplifying the integrand there, we can see here this is going to turn into a fairly straightforward integral to evaluate. So the square root of x squared for positive x values is going to be x. For negative x values, it's going to be imaginary. Well, when we square it, it becomes real, but we're not going to look at the square root function for negative values. And then we evaluate that like we would any other integral. So antiderivative of x is x squared over 2. We still have the pi. We're evaluating that from 0 to 4. So this is going to be pi times 4 squared over 2 minus 0. So 4 squared over 2 is 8. So our volume is going to be 8 pi. In our second example, it looks like the same problem. The difference here is that we are revolving now around the y-axis, and we're going from y equals 0 to y equals 2. So we're actually looking at the same part of the function, because in the last one we went from 0 to 4 along the x-axis. Now we're going from 0 to 2 along the y-axis. So the solid that we're going to get here is what happens when we take this region right here and revolve it around the y-axis. All right, so just kind of cleaning this up here. I'm going to mark my axis of revolution, and I'm going to draw a Riemann sum rectangle. Now, since we're revolving around the y-axis, my Riemann sum rectangle is going to be a horizontal rectangle. So the thickness of this, remember, is going to be delta y, which turns into dy in our formula, in our volume formula. And the radius here is going to be the x value. So this right here is the x coordinate. Let's do that. So this right here is whatever the x coordinate is. And so what we need to know is, what is x here in terms of y? So we're going to take the function y equals the square root of x, solve that for x. So we get x equals y squared. So the radius is going to be y squared. Now, you may be wondering, why do we have to figure out what the radius is in terms of y? Well, if we're revolving around this vertical axis and we're getting horizontal rectangles, that gives us delta y, which turns into dy in our integral. So if our integral is in terms of y, we need our radius in terms of y. So remember, our volume is going to be pi times the integral from lower limit to upper limit of the radius squared with respect to y. So in this particular example, we're going to have pi times the integral from 0 to 2 of y squared squared. So simplifying that, we have the integral from 0 to 2 of y to the 4th dy. Again, remember we have that pi there because it's part of the area formula for the circle. So if we are taking this Riemann sum rectangle and this is a radius and revolving it around the y-axis, we're going to get a cross-section that is a circle with that radius. So now evaluating this definite integral, pi stays out there. We're going to have y to the 5th over 5 evaluated from 0 to 2, which is going to be pi times 2 to the 5th over 5 minus 0. So it's going to be 32 pi over 5 will be the volume of that solid. And just to kind of get an idea of what that solid's going to look like, one thing I want to point out is you don't have to know what it looks like in order to do these problems, but this is going to kind of look like an upside down Hershey kiss. So we're taking this and revolving it around, so maybe a top or a funnel, or like I said, an upside down Hershey kiss. So we're finding the volume of this solid right here.